I thank you, all of you, for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem from the question paper CSIR National Eligibility Test held in the month of June 2023. This question is from the section Complex Analysis and it is related to the Taylor series expansion of a given function. This question is from part B, which is a multiple choice question, and it carries 3 marks. The question ID is 704035. This question is suitable for all these examinations. Right. The given question is: consider the function f defined by f of z is equal to 1 by, in the denominator, 1 minus z square for z belongs to C, the set of complex numbers, such that 1 minus z square not equal to 0. Which of the following statements is true? We are given 4 options. Option 1, f is an entire function. Option 2, f has a simple pole at z is equal to 0. Option 3, f has a Taylor series expansion. F of z is equal to sigma a n z power n, where the summation runs on n is equal to 0 to infinity, where the coefficients a n are recursively defined as follows: a0 is equal to 1, a1 is equal to 0, and an plus 2 is equal to an plus 1 for n greater than or equal to 0. Option 4 is same as option 3 except a1 is equal to 1. So, in the option 3, a1 was 0, and in option 4, a1 is 1, and the remaining things are one and the same. Right. We will now discuss the solution of the problem in detail. We are given f of z is equal to 1 by 1 minus z square, z belongs to the set of complex numbers, and 1 minus z square not equal to 0. Now, we write f of z is equal to minus 1 by z square plus z minus 1. And f of z is clearly analytic everywhere except at the zeros of the denominator, that is, except at z square plus z minus 1 is equal to 0. It's a quadratic equation, therefore there will be 2 roots, and the roots are given by z is equal to, and after simplification you will get minus 1 plus or minus root 5 by 2. So this function is analytic everywhere except at 2 poles, and one of them let us call alpha is equal to minus 1 plus root 5 by 2, and beta is equal to minus 1 minus root 5 by 2, and these are the 2 simple poles of this function. So f of z has 2 simple poles at alpha and beta. Now we call on the option 1, and option 1 says f is an entire function. Option 2, f has a simple pole at z is equal to 0. Now, clearly, f is not an entire function. Had it been an entire function, it is regular on the whole of the complex plane. It will not accept any singularities at all. But since fz has two simple poles at alpha and beta, f is not an entire function. So option 1 is not true, because f of z is analytic everywhere except at alpha and beta. And we have seen fz has two simple poles, alpha and beta. And z is equal to 0 is not a simple pole for that. So option 2 is not true, since fz has only two non-zero simple poles, alpha and beta, and z is equal to 0 is not a simple pole for f of z. Agreed. We continue our discussion in the next slide. So that is our option 3. The next one is option 4. Right. We continue. We have f of z is equal to 1 by 1 minus z square. Z belongs to C. 1 minus z square not equal to 0. And we have seen f of z is analytic everywhere except at alpha and beta. Notice that mod alpha is root 5 minus 1 by 2. It is positive. Mod beta is root 5 plus 1 by 2. It is positive. And mod alpha less than mod beta. Therefore, if you consider the open disk with the center 0 and a radius mod alpha, then fz is regular in that open disk. Now f of z is analytic, that is, and regular in the open disk mod z less than mod alpha. It is a circular disk with center 0 and a radius mod alpha. It's an open disk. So because it is analytic in the open disk, it accepts the Taylor series expansion about z is equal to 0. Therefore, f of z has a Taylor series expansion. Let us say fz is equal to sigma n is equal to 0 to infinity a n z power n, valid in this open disk mod z less than mod alpha. Agreed. But what is fz? 1 by 1 minus z square. That's equal to sigma a n z power n. Cross multiply. We'll get 1 is equal to 1 minus z square into sigma n is equal to 0 to infinity a n z power n. Multiply. You will write it as 1 is equal to sigma 1 into the sigma minus z into the sigma, that is minus sigma a n z to the power of n plus 1 minus z square into sigma, that is minus sigma n is equal to 0 to infinity a n z to the power of n plus 2. Thus we got this one. We take this and continue the discussion in the next slide. Right, that's what we have. 1 is equal to sigma n is equal to 0 to infinity a n z to the power of n minus sigma n is equal to 0 to infinity a n z to the power of n plus 1 minus sigma n is equal to 0 to infinity a n z to the power of n plus 2. Agreed. Now we equate the like terms. That means we equate the terms of the comparing the coefficients of z power k. That is what we mean by like terms. Comparing the coefficients of z to the power of k for k is equal to 0, 1, 2, etc. So let us say constant term z power 0, k is equal to 0. When k is equal to 0, the left hand side will give you 1 is equal to, the contribution will be, what we want is z power 0. Z power 0 will arise in the first sigma for n is equal to 0. So that is a naught. 1 is equal to a naught. And z power 0 doesn't arise from the other two sigmas. So 1 is equal to a naught. K is equal to 1. Comparing the coefficients of z on both sides. On the left hand side it is 0. On the right hand side, from the first sigma n is equal to 1, then it will give you a1z, that is a1 minus, from here when n is equal to 0, it will give you z power 0 plus 1 z, that is a naught. From the third sigma we don't get any contribution. and that will imply A1 is equal to A0 is equal to 1. So A0 is 1, A1 is 1. So look at our option 3. In option 3, A0 is 1, A1 is 0. Therefore, the option 3 is not true. Is not true. And this A0 is 1, A1 is 1 is present in option 4. But we have to show this reconciliation. But of course, without that also we will say that option 4 is true. But anyway, I will show you that relation. So, etc. Let k is equal to n. K is equal to n. The coefficient of z power n from left hand side is 0. From the right hand side, from the first sigma, n, that is an, minus the coefficient of z power n from the second sigma by taking in the place of n, n minus 1. So, an minus 1 minus the coefficient of z to the power of n from the third sigma by taking n is equal to n minus 2. That is, the coefficient is an minus 2. Thus, we got 0 is equal to an minus 1 minus an minus 2. That will give you an is equal to an minus 1 plus an minus 2 for n greater than or equal to 2. Now, for n greater than or equal to 0, what we do is, this will imply an plus 2 is equal to an plus 1 for n greater than or equal to 0. For n greater than or equal to 0. So that means writing in the place of n plus 2, we'll get an plus 2 is equal to an plus 2 minus 1, an plus 1, an plus 2 minus 2, an. So that's what, n greater than or equal to 0, in that case it will start. So that is precisely there in option 4. Thus, option 4 is true. The answer to this question is option 4. That is the detailed discussion of the solution of a problem from the section complex analysis, which is related to the concepts of Taylor series expansion. And it is definitely a moderately difficult question, but otherwise it is one can do in the examination hall. But normally, once you see f of z is equal to 1 by 1 minus z square, and if you are familiar with the Fibonacci sequence of numbers, and this 1 by 1 minus z square happens to be the generating function which generates the Fibonacci sequences. Therefore, by looking at that, you suspect that Fibonacci series sequence is arising in this. So that is there in option 4. So you can very easily tick option 4 without doing anything. If you know that 1 by 1 minus z square is the generating function which generates Fibonacci numbers. And the relations given in option 4 are precisely the definition of Fibonacci sequence. So the option 4 is, you can guess. So that is the detailed discussion of the solution of this given problem. I am sure that you understood the solution of this problem. I thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet once again in another episode of learning. I wish you all the best. Thank you.